Welcome to jconf 2020. My name is Mariano Gonzalez, and today we're going to be talking about native Spark executors on Kubernetes, diving into the data lake. So before we get started, a little bit about myself. I started doing Java probably around 15 years ago, and big data technologies 5-6 years ago with the Spark, Cassandra, Flink, just to mention a few. I'm also an open source contributor to some of these projects, but most importantly, I'm just a person trying to learn and share big data technologies and approaches. So hopefully the techniques that I'm going to be demonstrating today are going to be useful for you tomorrow. So before we get started, and since we are under a time constraint, I'm just going to fire a couple of Spark jobs that we're going to come later on and check them out. So I'm just going to fire all these 4 guys. All right. Okay, so let's get started. So what's the agenda for today? So before we get started, I want to do some clarification of some assumptions that we might have. What is the goal for today? Share some motivations why I decided to do this conference or this talk. A brief discussion on data lakes, the challenges that traditional data lakes have, and a quick description of the proposed solution of how we can solve these challenges that the traditional data lakes have. And finally, we're going to be doing a demo that I already started, as you saw, but later we're going to discuss it in more detail. Okay. So the goal for today is ingest, process, and surface large amounts of data in an accessible way. So this diagram shows the traditional architecture of any data pipeline, where you have different data sources in different file formats, and you just want to process it, transform it, and store it somewhere so the user can later, or the data scientist, ML engineer can later query it. Okay. So why are we doing this talk, or why I decided to do this talk? Well, setting up an infrastructure with a successful infrastructure with the Spark is very, very complicated. So it's a complicated relation with the Spark infrastructure. I have tried several, not several, but a couple of enterprise distros of Spark, such as Cloudera, DataStax, and managed services such as EMR from AWS, HD Insights from Azure, and all of them have weakness and strengths, pros and cons. So today the goal is search a new way, an elegant way for setting up a Spark infrastructure on top of a data lake. That's motivation. Okay, but how did the term come from, or where did it come from? Well, the term data lake was introduced by James Dixon, who was CTO at Pentaho during 2010. And I really like this definition. Yeah? So if you think of a data smart or a data warehouse as a stored bottled water, where the water is already cleaned and packaged and structured and ready for consumption, you can think of a data lake as if it was a large body of water in a more natural state. So what makes up a data lake? What are the characteristics of a data lake? Well, first of all, consolidation. A data lake should be a place where I can load or onboard a variety of different data sets without disrupting existing workflows. I don't want to disrupt the workflow of an ML engineer. I don't want to disrupt the workflow of existing software engineers. So this onboarding of new data sets should be easy. Okay, data lakes should be able to store data at any scale. You will see that the vast majority of data lake technologies normally are backed up by cloud object storage services, such as S3, that offer pretty much virtually unlimited space at a very low cost. Locate, curate, and secure data. Having a centralized data lake makes it easier to track what data do we have, who is accessing, how we are storing it, and what is being used for. And agility, extending the existing architecture to support different workloads should not be difficult. Okay, but what are the difference between a data lake and a data warehouse? Well, first of all, a data lake is not a replacement for a data warehouse. They are supplemental technologies that have some overlap. The main characteristic of a data lake is that you can store the data in a native format. That means that the data can be loaded faster and quicker if we don't need to go through this initial transformation. I can just dump my Avro files, my JSON files, my CSV files. The raw data just goes there directly. Whereas for traditional or relational databases, the data will need to be processed before and manipulated before being stored. Flexibility when accessing the data. If we don't need to go through this initial transformation process, this is more flexible than the traditional DEI architecture where this needs to happen. So data scientists and engineers can start making sense of this data faster. And probably the most important one is schema on read. For those who are familiar with traditional or relational databases, normally you need to define the schema on write before, right? And this requires an upfront data modeling exercise where you define your schema, primary key, tables, and all that. But with a data lake, this is a little bit different because the schema is on read. Each client can have their own schema, and it can be tailored on a case-by-case basis. The schema can evolve with the application little by little, and the data can be processed as needed. So if I keep adding columns, that is not going to affect my existing clients or the existing clients that are consuming these tables. So what are the operational complexity of maintaining a data lake architecture? Well, some cluster management solutions, for those who are familiar or heard about Yarn, that is one solution, and the other one is the traditional Spark standalone cluster. But both of these solutions offer some challenges. First of all, or the most important one, is resizing the cluster normally is difficult. Normally, once you define the cluster, it remains that size, or you need to have some downtime, add the nodes, update files, and then resize the cluster. If you need to scale, if you need to scale the cluster, you normally end up scaling compute and the storage at the same time, even though that you might need only one of them. It's normally weird that you run the Hadoop open source distribution. You normally end up running a Cloudera distro, a DataStax distro, Hadoop, and that normally comes bundled with the specific libraries from the vendor. So that means you're going to be behind the Spark open source distro, or wait until the vendor patches or updates the runtime. There is a lack of resource allocation. This goes hand by hand with the cluster resizing difficulties. You cannot say, hey, at 12 where we have this huge user peak, I want to add more resources for just these 2 hours where it is when we are having all these users on our side. That's not possible. Once the cluster is set up, it's that. And also, there is a security setup labyrinth. You are going to be integrating with AD or Active Directory, Kerberos, and Centrify to make them play well together. And if you are doing a Spark standalone clusters, maintaining different runtimes is going to be very, very difficult because these binaries need to be distributed across all the different members of the clusters. So if you have a JSON library, let's say Jackson 2.5, and another Spark job is using 3.x, probably the 2.5 is going to need to upgrade, or the other one needs to downgrade because these runtimes are shared across this cluster. Or if you decide to do Yarn and have more isolated containers, and the amount of XML files that you are going to be configuring is going to be massive and are error prone. And also the static architecture resulting in unextendable pipelines. Normally you first define your cluster to support batching, but later you need to add the streaming. That's going to be difficult for us because once you set up your EC2 instances or your boxes of a certain size, it's going to be difficult to modify them to support different use cases or workloads. Okay, so where did this inspiration came from? Well, Airbnb released this one paper about their initial data infrastructure in 2016. And one thing that I want to highlight, you can see how there is a separation of different clusters. So, for instance, this is what they call at that time the Gold cluster. It's pretty much the cluster that is doing all the ingestion process. And the Silver cluster is the one that was doing all the aggregation. So later Spark via Spark SQL can later come and query these guys. So something to highlight about this is that if for whatever reason the ingestion process is taking a lot of resources, that's not going to affect any of the aggregations that are happening on the Silver cluster, and vice versa. If somebody issues a massive query that is pulling a lot of data, the ingestion process will continue as it is. There is no they are not going to be competing for compute resources. So this is the first approach where there was a clear separation of compute for building different pipelines. Then Databricks with Delta Lake in 2019 leveraged some of these ideas, but added another, let's call it another area or another zone called the Silver one. So now we have ingestion where the raw data exists, which is what they call the bronze tables. The refined tables, which are the Silver tables, and the feature or aggregated tables, which are the gold tables. And this architecture normally supports any type of workload, and it's backed up by the traditional Hadoop HDFS file system, the Azure Data Lake Storage, or Amazon S3. So these are the two main ideas that I put together and decided to do and come up with a solution that I'm going to be presenting now. So this solution is just a central place where engineers and data scientists can collaborate and run diverse workflows. So how are we going to do that? Well, we're going to be leveraging Kubernetes to do all the cluster management and scaling. We're going to continue using Spark for doing all the transformations. We're going to be leveraging managed services so we can remove the burden of managing complex infrastructure, and we are going to continue using the same concepts of bronze, silver, and gold pipelines that Data Lake and Airbnb infrastructure first come up with. And the good thing is that the store and compute services are going to be managed services, in this case Amazon EKS and Amazon S3. This architecture also can be deployed to GCP or Azure. They are equivalent services for the two of them. Okay, so how did we get to this solution? Well, first of all, cloud object storage is recommended because several reasons. First of all, they offer up to 11 nines of availability. You won't see S3 going down quite often, right? And when you see it, half of the internet normally goes down, like happened a couple of months ago. And normally, this type of solution is scalable and is very well suited for storing vast amounts of unstructured data. With virtually unlimited capacity. It's also affordable. Normally you will pay 0.01 cents per gigabyte each month. It's secure, it's granular all the way down to the object level, and it's integrated with our solution, which in this case is Spark. Spark offers first-class settings and support for pretty much all the S3 APIs, and yes, it's a managed service. The solution for compute, how did we get to this solution? Well, Kubernetes has positioned itself as the de facto container orchestrator, and Spark continues to be the tool of choice for running big data workloads. So why don't we run Spark on Kubernetes? No, if we do that, we no longer need to have a different infrastructure for running our our Spark cluster is extendable, as we're gonna see later on. And most important, all the runtimes are available via Docker images, so I don't need to patch the cluster or depend on the vendor to update the runtime. We are just going to be deploying Docker images, and developers are empowered to update these runtimes with new Scala, Python, or R libraries. And yes, it's also a managed service. So why do we want to use Kubernetes as our cluster manager? Well, the main reason is resources are better optimized. I don't need to run a cluster that is doing nothing at midnight, right? So if I can have the auto scaling that Kubernetes offers and shut down all the pipelines that are doing nothing, that's a good reason for doing this. And also we can leverage some of the cool features that Kubernetes offers out of the box, such as namespace quotas. So I can have one dedicated namespace for my pipeline, my goal pipeline, with the specific quotas, pluggable authorization, so I can have my RBAC roles for my Spark application for all these different pipelines, and I'm pretty much all set. So there is no complicated stuff such as Active Directory, Centrify, and all that, because we're leveraging a very well secure model from Kubernetes. So how does this actually work? Well, for those who are familiar with the Spark Submit is the binary that ships with any standard distribution of the Spark. And normally when we are targeting a Kubernetes cluster, the first thing that happens, the Spark Submit talks to the API service scheduler from Kubernetes, spins up a Spark driver within a pod, and then depending on how many executors you define, those are the number of pods that are going to be spun up. So the process is very, very straightforward. Spark Submit talks to the API scheduler from Kubernetes. The API scheduler creates a Spark driver pod, and depending on how many executors you define, those are the number of pods that you're going to be creating. It's important to mention that all the logs remain on the Spark driver pod, so you can see the exit status of your job. The executors disappear immediately after the job is done, but the Spark driver pod will remain there, and you can and it can be garbage collected or manually removed. So the advantage of this solution is that we are decoupling effectively compute and storage by having Kubernetes as our compute engine and S3 as our store engine, and they can scale completely independently. But the advantages of this solution is that the Kubernetes engine is available in all major cloud providers, AWS, GCP, or Azure. We can run multiple data science and engineering workloads, which can be CPU intensive. I can have EC2 instances that are beefy or bigger, that are optimized for compute. And I have the storage intensive backed up by S3. Also, this solution minimizes all the burden of having to maintain our own infrastructure. There is all this dynamic and lightweight scaling, right? And since we are deploying Docker images, there is no need to patch the cluster. Developers are responsible for updating their runtimes and their own libraries, either Scala, Java, Python, or R dependencies. So this is something really cool. We no longer need our SRE friend to update the cluster, right? Something really, really cool. And finally, some of the solutions, the advantages for the storage. Well, the storage object is a managed service also. You can ingest different format types such as structured, semi-structured, unstructured data, and most importantly, real-time and historical data remain available without many changes. There is no need of doing rollups from your historical data into another data storage. So for instance, if you are doing Snowflake, probably you are doing all your ingestion into your data lake or your data warehouse, but you're probably going to be rolling up all these aggregations into MySQL so they don't charge you per query, right? So these are some advantages of these solutions, compute and storage. So Now, this is the architecture diagram that we're going to be demoing, the application that we're demoing. We're going to be connecting to the streaming API from Twitter, and we're going to have a Python Spark job that is going to be listening for that TCP host or socket. So all the tweets that we ingest and filter based on a term are going to be published to a TCP socket, and then our first Spark job is going to come and ingest those and raw JSON and save it to the bronze bucket. Later, we're going to have a Scala app, the transformation app that is going to be reading this JSON file and transform it into Parquet or columnar format. And later, we're gonna be playing with the third application that is gonna be reading this columnar format, but just preparing the aggregation table. And later, we're gonna run also Zeppelin on Kubernetes to do all this data visualization. All right. So also the last thing that I want to mention is it's a common misconception that a data lake is just a giant bucket. That's not true. You can order your buckets very nicely as we show, and if we put the two papers from Airbnb and Databricks, we just want to preserve the same naming convention. Bronze bucket for all our raw data, Avro, JSON, CSV. Silver bucket for all the columnar data, Parquet, org, and our aggregated data that can be Parquet or Arrow, Apache Arrow for our gold bucket. So that's not true that you just need a giant bucket. No, you can organize it nicely and effectively. Okay, so now it's time for some code. All the code is available under this URL. Please feel free to download it, PR if you see something wrong. So let's get started. The first thing that I want to show you here is that I have three buckets, bronze, gold, and silver. I have already ingested a little bit of data that we just started moments ago. So first of all, the bronze data, here's where we are storing all our JSON files. And this is the first step of our application. And then later, we have all the silver data. Here we're going to see Parquet files that are just the transform JSON into the columnar format. And then later, we're going to be talking about the gold bucket. But first, let's talk a little bit about these two applications. So the Twitter producer is nothing but just a listener where we have an on success and on error. On success, we are just going to publish, we're going to batch those tweets on a sizes of 100 and send it to the TCP socket. Very, very straightforward, nothing spectacular here. And the interesting part comes here. We're going to have our first streaming job that is going to be listening for that TCP socket. And then later is going to be persisting those into the first bucket, which is in this case, where it's going to be reading, persisting this into the first bucket, which is the bronze bucket. And then later on, we're going to have our transformation app, which is an Scala app. This is for this application, we're going to be leveraging some of the built-in JSON functionality that Spark offers. And this is a JSON path expression that allows us to access some of the fields of the JSON file that we save on the bronze bucket. We want to save the timestamp, the extended tweet, and the text of the tweet. Sometimes the tweets don't come with the extended tweet, so that's why we need to look for both of them. The user, just in case we need it. And later we have a regex expression that is going to search for all these tweets that start, or text in the tweet that starts with the pound sign, and those are going to be the hashtags. And later we're going to be using a very, very nice framework called Spark Barrier, which is a layer of abstraction on top of a Spark streaming that allows us to define the source. which is in this case the streaming data lake. Where are we going to be reading from? The transformation that we just talked about it, which we are reading the JSON and transforming into Parquet, and how we're going to be writing. Here we have the silver bucket that we're going to be writing Parquet. So, and this is a very, very straightforward way of doing Spark streaming and persisting in Parquet format. So as you can see, this just keeps growing and growing, and let's examine. Okay, now that we have here our first aggregation, well, actually we have two of them. That's pretty cool. As you can see, our jobs continue. I'm just gonna show very quick some of the logs. So far we have processed. Let's see if we see the numbers here. Well, we cannot see the number, but these are, here we are. So far we have processed a good amount of tweets. You saw it there, over 40,000 of them. And now let's go to Zeppelin. So the first step that in order to do all to show these aggregations. First, we need to load some Spark configurations such as S3 credentials, and then later we can come and query our gold bucket and prepare normally the aggregations, or visualize the aggregations that we save on the gold bucket. So we're gonna run this, and we're gonna just pull the hashtags and the number and the counts. So here you can see all the Spark jobs that I'm running here. An aggregator for the R app, the streaming job with 2 executors each, the transformation job with 2 executors each. And here you can see that I'm running. This is the job that is run from just Zeppelin. And here we can see finally all our aggregations. And finally, we're gonna just visualize this. Here we see the Spark job running. And finally, we can see that today is trending Meadow, Trump is not like you, Reiki, Moscow Mitch, and several other. And we can see all the counts that we see here. I forgot to talk briefly about the R application. Let me do that really quick. The R code is really cool because it looks pretty much like a Scala. So here we're just saying, we're telling Spark, hey, we don't want to save any message that comes after 5 minutes. We're just going to discard it just in case we're receiving really old messages. And later we are just going to do a count and a group by based on the number of the counts of the hashtags that we find. And later we are going to just persist it. So the code looks really familiar to the Scala code. And as you can see, it's really straightforward. There is nothing complicated with Spark streaming. The APIs are really solid. And that's all what I have for you. I hope you have fun during this exercise. If you have any questions, I will be more than happy to talk about them. Here is just a very detailed slice of each of the applications that we just deployed. As you can see here is the Spark Twitter producer, the consumer, the transformation app that we just deployed, the R application that reads from the bucket silver to the gold bucket, and finally the visualization via Zeppelin. It's important to mention that we are also running the latest version from Zeppelin, and it's also running on Kubernetes. So we just have proof how to run a fully containerized data pipeline on Kubernetes. Future work. Google has been developing what they call the Spark Kubernetes operator. So instead of running like I'm running right here, these shell commands where I specify each of the flags for Spark, You can have YAML files and configure those Spark jobs in a more easily way. And that's all what I have for you. I hope you have fun during this talk, and I will be online replying to your questions. Thank you so much for attending this talk.